Okay, so we'll talk in this lecture about the relationship between continuous time and discrete time frequencies. Just a reminder, we know that if we are talking about sampling theory, then we are given a signal, we pass it through a continuous to discrete time. With sampling period t, we get Gn. And we know that under what conditions the samples don't lose any information about the original signal. But the thing that we don't really know about is how are the frequencies in the continuous time signal related to the frequencies in the discrete time signal. The continuous time signal frequencies are given by the continuous time Fourier transform, and the discrete time signal frequencies are given by the discrete time Fourier transform g of e to the j omega. And of course, the frequencies of the continuous time signal go from minus infinity to infinity, or if it's band limited, from minus omega m to omega m. The frequencies of the discrete time signal, on the other hand, only go from minus pi to pi, and then they repeat themselves. So what is the mapping of the continuous time frequencies to the discrete time world? That's the missing piece that we haven't talked about so far. If you record my speech, and let's say I have some really high energy present at 3 kilohertz in continuous time, when you look at the samples of my speech, where will those 3 kilohertz frequencies appear in the discrete world? There has to be some mapping, and that is what we are going to learn about, that when we sample a signal Ga of t with frequency 2 pi over t, what is the relationship between the frequencies of the continuous time signal, which are given through the Fourier transform in the continuous domain, and the Fourier transform of its samples. Now, to do that, we again remind ourselves of the impulse sampled signal. This impulse sampled signal will keep on appearing throughout the discussion about sampling theory. So impulse sampled signal, we know that this is given by summation n from minus infinity to infinity g of n delta of t minus nt. Impulse sampled signal is nothing but a train of impulses where the area of each impulse is proportional to the sequence or the signal value at time nt. And we also know the Fourier transform of this impulse sample signal. The Fourier transform of this impulse sample signal is given in terms of the continuous time signal. We talked about it earlier. It's scaled by t. You get multiple copies of your original Fourier transform, Ga of j omega minus k omega t. So using this expression, what we'll end up doing is relate the Fourier transform of the samples of my signal to the Fourier transform of my continuous time signal. Okay, so we want to look at the Fourier transform of the sequence Gn. And for that, we just first look at the definition. So the Fourier transform of Gn is g e to the j omega. So it's summation from n minus infinity to infinity g of n e to the minus j omega n. This is the definition. I have not done anything fancy here. This is the definition of the discrete time Fourier transform. Now, let's look at this expression of the impulse sample signal and take its Fourier transform. So I'll write this in, I'll take the Fourier transform of this summation formula. I'll take the Fourier transform of Gp of t, which is equal to the Fourier transform of sum n from minus infinity to infinity, g of n delta of t minus nt. I'm not writing the Fourier transform formula in this way. We'll relate it to that later. If you remember, we had derived that Fourier transform formula using another trick using the Fourier series. We'll relate it to that, but right now we'll just directly use the Fourier. This is the properties, we'll just use the properties of the continuous time Fourier transform. So since Fourier transform is linear, I'll take it inside the summation Fourier transform of g of n delta of t minus nt. Now this is a continuous time Fourier transform. Right? I'm taking the continuous time Fourier transform. So for that perspective, gn is just a constant. It's just a number. So I get summation n from minus infinity to infinity g of n Fourier transform of delta of t minus nt. So using the fact that the Fourier transform of delta of t is 1, and the time shift property, which means the Fourier transform of delta of t minus nt is e to the minus j omega nt, we see that Gp of j omega is equal to n from minus infinity to infinity g of n e to the minus j capital omega nt. And I'm going to write it in a little bit different way, and you will see why. G of n e to the minus j omega capital T times n. So let's look at this part and this part and compare it to this Fourier transform of your discrete time formula. What do we see? That the Fourier transform, my discrete time Fourier transform, is summation n equal to minus infinity to infinity. My continuous time Fourier transform is also n equal to minus infinity to infinity. You have gn, you have gn, and then you have e to the minus j little omega n here. But in this case, you have e to the minus j capital omega tn. This means that the Fourier transform of my discrete signal is nothing but the Fourier transform of my impulse sample signal j omega, where capital omega is replaced by little omega over t. If I replace my capital omega here with little omega by t, then I get back the formula that is given here, this formula. Right? So just to repeat, the Fourier transform of my sequence is equivalent to the continuous time Fourier transform of my impulse sample signal, but with capital omega replaced by little omega over t. Okay. And if I use the other property that my GP of j omega equals to 1 over t summation k from minus infinity to infinity GA of j omega minus k omega t, then I can now, using these two formulas, this one and this one, I can also write the discrete time Fourier transform of my sequence as a function of the continuous time Fourier transform of my input signal. What will that be? I simply replace capital omega in here by little omega over t. So replacing, let's call this star, replacing capital omega equal to little omega over t in capital star, we get g of e to the j omega equals 1 over t summation k from minus infinity to infinity GA of j little omega over t minus k omega t. And I'll write that down in a more nicer fashion. I'll write omega t as 2 pi over t. So it will be j omega minus 2 pi k over whole t. Okay. So this is the expression that relates the discrete time Fourier transform of your samples to the continuous time Fourier transform of your input signal. There are two ways of going to the discrete time Fourier transform of your sample. You can first figure out what is the Fourier transform of your impulse sample signal and then simply replace capital omega by little omega t, or you can work directly with this formula. So let's take a look at what is the k. Let's first look at the intuitive meaning of going from GP of j omega to g of e to the j omega. Okay, so we are going to look at the relationship between Gp of j omega and g of e to the j omega. The mathematical relationship is clear. It's g e to the j omega is Gp of j omega with capital omega replaced by little omega over t. What this means is that in this chain diagram of you start with Ga of t, then you go to Gp of t, and then you go to G of n. We understand that the relationship between the frequencies of this Gn and the frequencies of Gp of t is given by this expression. So what does this mean? This means that the frequencies of the continuous time Gp of t and the frequencies of the Gn signal, they are related by simply a scaling of your frequency axis. Okay. So assume that the frequencies of your continuous time signal GP of t, they are given by this. They are given like this. You have one main copy with a scaling of 1 over t, and assume the original signal was band limited. Then of course you get a second copy at 2 pi over t, and you have another copy at minus 2 pi over t, and so forth. Right? So this is what your GP of j omega looks like. Of course, it's a periodic repetition of your main Fourier transform, where the repetition is every 2 pi over t intervals. This is your capital omega axis, which is in radians per second. Now, what this expression is saying is that the Fourier transform of your discrete time signal is nothing but you replace your capital omega axis by little omega over t axis. So g of e to the j omega means replace capital omega with little omega over t. So I just replace this by little omega over t. So now this axis is effectively little omega over t axis. So if I want to write it as a function of just little omega, I will multiply my entire axis by capital T. I have right now little omega over t axis. I want a function of little omega, so I'll multiply my entire axis by capital T, and my new Fourier transform, if I am scaling just my frequency axis, depending upon the value of t, so this point will become omega m capital T. This point will become minus omega m capital T. The height at this point, of course, will stay at 1 over t. Now, what will be the point? What will 2 pi over t become? So this point, 2 pi over t, will become 2 pi, minus 2 pi over t will become minus 2 pi. And this is now little omega axis, and the units of this are just radians, because you have multiplied by t, which has units of seconds. So if you are ever given the frequencies in GP of t, what that means is that the frequencies of your discrete time signal are nothing but scaling of your frequency axis. Okay. In particular, we know that if you satisfy the Nyquist criterion, then omega t by 2, which is equal to pi by t, and omega minus omega t by 2, which is equal to minus pi by t. There is no overlap across this pi by t point. That pi by t point in discrete time will get mapped to pi, and minus pi by t point will get mapped to minus pi. So the relationship as we go from GP of t to g of n, the frequency axis gets scaled by capital T. That's the only relationship that exists between the frequencies of the continuous time signal GP of t and the discrete time signal g of n. Okay. So now we want to finally look at this relationship gn and ga of t directly. I'm given continuous time signal, I sample it, I get a discrete time signal. How do the frequencies in my continuous time signal get mapped to the discrete time signal? Okay. And for that, we'll have to look at this formula, which I'll call double star. So what is this formula saying? It is very similar to something we had seen earlier for the relationship between continuous time frequencies of my original signal and the continuous time frequencies of my impulse sample signal. The first thing is that you are looking at these multiple copies. You have this summation. This should be k, not n. You are looking at this summation, which means that your original Fourier transform, your original frequencies, you get now multiple copies of those frequencies, which is what you would expect because the discrete time signal has periodic frequency. So you want multiple copies. So you get multiple copies of your original frequencies, and each copy now has an amplitude scaling of 1 over t. It has an amplitude scaling of 1 over t, and it has a frequency scaling by a factor of t. So your frequencies are also being scaled, and once you do the frequency scaling, then your multiple copies are separated by factors of 2 pi. Okay. So those are the three main things that you need to remember from this formula. We can write that down more formally. So this is one, but now as we go from the original signal GA of t to G of n, which is just samples of GA of t after every t seconds, three things happen. The first is that you have scaling of amplitudes of frequencies by 1 over t. Secondly, you get scaling of the frequency axis by capital T. And then the third is you get multiple shifted copies of the scaled amplitude and scaled frequency axis that are separated by multiples of 2 pi. Okay. So let's say now we can skip the middle part of GP of t. Let's say that you had a continuous time signal GA of t and its Fourier transform GA of j omega looked something like this. And let's say that this is 5 kilohertz endpoint, and this is minus 5 kilohertz. And this height, so this, make this uniform. Let's say the height is 3. And we sample now this signal using sampling frequency fs equals 15 kilohertz. And you are asked, what will the Fourier transform? You now have the samples. You computed Fourier transform of those samples. What would the Fourier transform look like? So what is G E of j omega? So of course the formula is simply given by this double star expression. But to be able to visualize it and understand what is happening to individual frequencies, all we have to do is look at these 3 points that we had written earlier. So the first point was you get a scaling by 1 over t. So let's put down the little omega axis. Let's say you have, the first part is you have a scaling of amplitude of frequencies by 1 over t. So instead of 3, you get 3 divided by t, which is 3 times 15,000. The second is you have scaling of the frequency axis by capital T. So these endpoints, the 5 kilohertz, now the scaling, we have to be careful. We want to do it in radians per second, so we'll do that in 5 times 2 pi. So the frequency axis gets scaled by a multiple of capital T. So what will this 5 kilohertz or 10,000 pi radians per second, where will that go? So my capital T is 1 over 15,000. My sampling frequency is 15 kilohertz. So my capital T is 1 over 15,000 seconds. So this point will go to, this point will be 10,000 pi times capital T, which is 1 over 15,000, which will be equal to 2 by 3 pi. Similarly, this minus 5 kilohertz will be minus 2 by 3 pi. And once I do the stretching, whatever is the shape of the Fourier transform, I'll get, or in this case contraction, whatever is the shape of the Fourier transform I get. In this case, if it's a straight line, I'll still get back a straight line. So these are the first 2 points that we have addressed. We have done the scaling of both the amplitude and the frequency axis. Now the third point is we actually get multiple copies of this same thing shifted by multiples of 2 pi. So my final g of omega will, g of e to the j omega will be, now I simply take this thing and I shift it by multiples of 2 pi again and again. So I have one copy is here, then the other copy is at minus 2 pi, 2 pi. So this is a copy at minus 2 pi, this is a copy at 0, at 2 pi. The height of each one of these things is 45,000. And of course, this keeps on repeating. This is the little omega axis. So this is 2 by 3 pi. This is minus 2 by 3 pi. What will this point be? It will be 2 pi minus 2 pi by 3. Because the distance from 0 to this endpoint is minus 2 pi over 3. And similarly, this point will be minus 2 pi plus 2 pi by 3. Okay. And pi will be somewhere in the middle. So this is pi and this is minus pi. Now this is the case. Of course, we see that this frequency axis scaled and amplitude axis scaled copy doesn't overlap with each other. They stay away from pi. If things go across pi, then you start getting overlaps of different copies. Now that has happened here because of the reason that I am satisfying the Nyquist criterion. My maximum frequency was 5 kilohertz and I'm sampling at 15 kilohertz. Okay. In particular, this pi point in continuous time, it always corresponds to the pi by t point in continuous time, which in this case will be equal to, which frequency this will be equal to? This will be a 10 kilohertz frequency. And minus pi is minus 10 kilohertz frequency. So this pi will be pi by t, and since I sampled at 15 kilohertz, this actually should be 7.5 kilohertz. So this pi point will always be 1/2 of your sampling frequency. So minus 7.5 kilohertz will be minus pi. And of course, you won't have any overlap of different copies as long as you're satisfying the Nyquist criterion. So let's now assume that we did not satisfy the Nyquist criterion. What will this thing look like? So a second version of this problem will be that now my sampling frequency, I have the same spectrum. I still have the same signal. This is my signal's Fourier transform. But now my sampling frequency, that Fs, let's assume that that is equal to 8 kilohertz. Which means that T is equal to 1 over 8,000. Now we know that in the continuous time sense, we understand that we'll have aliasing. But what does it mean in terms of discrete frequencies? Where will the aliasing take place in the discrete frequencies? Again, we just have to remember these three main points. So to do that, we again just first look at point 1 and 2, which is amplitude scaling by 1 over t and frequency axis scaling by capital T. So what do we get? Of course, the height now will be 3 times 8,000, that will be 24,000. Okay. So that's 3 over t. This endpoint will be now 5 kilohertz, so 10,000 pi multiplied by t, that is equal to 10,000 pi over 8,000 or 5 by 4 pi. And this endpoint will be minus 5 by 4 pi. Of course, 5 by 4 pi is bigger than pi. So you are already seeing that your main copy is stretching beyond the pi region. Now when you take multiple versions of this and add them all up, you will have overlap of different copies. So now I take care of point 3, which is multiple copies shifted by 2 pi. And that's my Fourier transform of g of e to the j omega. So if I do that, my main copy is going from minus 5 by 4 pi to 5 by 4 pi. My pi is here, and my minus pi is here. Now my second copy, so the height of all these things are 24,000. My second copy is at 2 pi, but that copy will overflow into my main copy because this point is 2 pi minus 5 by 4 pi. Similarly, I'll have a copy at minus 2 pi which will overflow into this other copy. So if I look at just the principal period of my Fourier transform, and then we can just do the repetition. If I just look at from minus pi to pi, what does my Fourier transform look like? I'll have 24,000 up to a certain point. And after that, because I have summation of these two pieces, I'll get 2 times that, so I'll get 48,000. And of course, after this, I'll just have things repeated. So this is minus 2 pi. Sorry. Minus 3 pi. And so this is minus pi, pi, 3 pi. Okay. So this is effectively what we were talking about aliasing in continuous time. You see the effect of that happening in the discrete time too. You see that in the previous case, we had a spectrum which looked very much like the original signal. This is the discrete time. This is the main fundamental frequency part of my spectrum. It looked very similar to my original spectrum, with, of course, scaling of the frequency and the amplitude axis. But whenever I did not satisfy the Nyquist criterion, I see that I have now a spectrum which in the principal period doesn't even look like my original spectrum. Now let's just solve this problem. So this point is where the overlap started. This is 2 pi minus 5 by 4 pi, and this is minus 2 pi plus 5 by 4 pi. So this is what your end spectrum will look like. So what is the meaning of these things is that you are now able to relate the continuous time frequencies to your discrete time frequencies. Okay. In particular, if we assume that the Nyquist criterion is satisfied and there is no So there is no aliasing. In that case, actually, the discrete time Fourier transform of your signal gives you all the information about the continuous time Fourier transform of your continuous time signal. So g of e to the j omega tells us everything about GA of j omega. So let's do it in a couple of ways. So first of all, let's assume that our sampling frequency is, let's say, 40 kilohertz. So my T is 1 over 40,000. And Nyquist criterion is satisfied. Now, using that fact, someone shows you compute the samples of your signal, you compute its discrete time Fourier transform, and you find out that g of e to the j, let's say pi by 4 equals 0. So your discrete time signal Gn has no frequency component of pi by 4. So your Fourier transform at pi by 4 is 0. Your discrete time signal has no frequency at pi by 4. What does that tell you about your continuous time signal? Using the fact that your frequency axis is getting scaled by capital T, this means that this pi by 4 radius frequency in discrete time, this corresponds to, this is obtained using omega naught times T. So pi by 4 came about by multiplying some frequency with capital T. Your frequency axis is getting scaled by capital T. So pi by 4 corresponds to multiplication of some continuous time frequency with T. So this means that the frequency that gave rise to pi by 4, that frequency is pi by 4 capital T, or that's pi by 4 times 40,000, or that's 10,000 pi, or 5 kilohertz. So that 5 kilohertz continuous time frequency gets mapped to the pi by 4 discrete time frequency. We already now know that from our earlier discussion. In this formulation, we are going backward. We are asking which frequency got mapped to pi by 4. It's a 5 kilohertz frequency. So if 5 kilohertz frequency got mapped to pi by 4, the other thing we know is that whatever was that 5 kilohertz, the amplitude of that gets multiplied by 1 over t. But we are saying that our discrete time amplitude is 0. What does that mean? That the amplitude of my continuous time frequency at 5 kilohertz must also be 0. So what this says is that the continuous time signal has no 5 kilohertz component in it. So the relationship that we have learned between the continuous time Fourier transform or the discrete time Fourier transform helps us address which frequencies are present in my continuous time signal by just looking at the Fourier transform of my discrete time signal. If my pi by 4 frequency has zero amplitude, then that means that my continuous time 5 kilohertz frequency, there was no such component there. So another version will be, let's say we see that g of e to the j omega equals to 0 for all omega, let's say all omega greater than or equal to 3 pi by 4, right, in the principal period. Of course, it can't be 0 forever because of the periodicity of the discrete time Fourier transform. So what all we are told is that if I look at between minus pi and pi, then the Fourier transform between 3 pi by 4 to pi and minus pi to minus 3 pi by 4, this is exactly 0. What does that tell me about my continuous time signal? Well, again, we just have to do a reverse mapping. So this 3 pi by 4 point, this point means which frequency in continuous time? Again, we'll just now divide it by t. So we are just doing the reverse of what we had to do when we are coming from continuous time to discrete time. So we get 3 pi by 4 times 40,000. So that's 30,000 pi, or that's 15 kilohertz. And of course, pi is 20 kilohertz. Pi is always 1/2 of your sampling frequency. Similarly, this point is minus 15 kilohertz. So this knowledge that your discrete time Fourier transform is all 0 between 3 pi by 4 and pi means that your continuous time signal has no frequencies between 15 kilohertz and 20 kilohertz. So the relationship between the discrete time Fourier transform of your discrete time signal and the continuous time Fourier transform of our continuous time signal helps us do this mapping between the Fourier transforms of the two signals to what's the mapping in frequencies, what does it mean in terms of the real world that I was sampling. So a continuous time frequency gets mapped to that. So let's call that omega naught. The mapping to discrete time is omega naught times t. If you ever forget, a rule of thumb is that the units of continuous time frequencies are radians per second. So you have to multiply radians per second with seconds to get radians. Okay? And then if you are given a discrete time frequency little omega naught, so the reverse mapping is it gets mapped to little omega naught over t. So just like we did earlier, 3 pi by 4, what does that correspond to? It corresponds to 3 pi by 4 divided by t. So radians, you have units of radians, you want to go to radians per second, you have to divide by t. Now this is the mapping when we have a continuous time signal and we have an ideal sampler and we get g of n equal to ga of nt. Okay. In this case, being able to seamlessly map the continuous and discrete time frequencies, that is one of the most fundamental tasks that you need to do as a signal processing person. Now the other question we can ask is the reverse of that. Given a discrete time signal, g of n, which may or may not have come from a continuous time signal, doesn't matter. Given a discrete time signal g of n, if we pass that g of n to a discrete to continuous converter with some sampling period t to get ga of t, then what is the relationship between the reconstructed, so let's call it actually gr to relate it to reconstructed signal, gr of t, then how is the continuous time Fourier transform grj omega of gr of t related to the discrete time Fourier transform g e to the j omega of gn. Okay. And this is an important case. For example, if you are dialing your phone, right? You press these buttons for different numbers, and those numbers actually get converted into frequencies that get transmitted so that your phone company can understand what numbers you pressed. It's called DTMF tones. And we'll have a lab about that, which will stress this point further. But right now, we just want to ask, if we are given a GN, a discrete time signal, and we do its reconstruction, an ideal reconstruction, what's the relationship of the output continuous frequencies with the input discrete frequencies? So it's the opposite of what we were discussing earlier. Now, to look at that problem, we have to remind ourselves of the reconstruction formula. So one of the key things that is inside the discrete to continuous converter is reconstruction filter. So we have a reconstruction filter which has an impulse response hr of t and the Fourier transform of hr of j omega. We can of course talk about an ideal reconstruction filter. So we can talk about the ideal reconstruction filter, which is hr of j omega equals to t for omega less than or equal to pi by t and 0 otherwise. Okay. So for the time being, if we don't use the ideal reconstruction filter, we just say it's some filter, we know that the reconstruction GR of t is given by this interpolation formula G of n HR of t minus nt. So you take the impulse response, you shift it by multiples of t, and then you simply scale each impulse response by the value of your sequence Gn. Okay. So if you want to relate the Fourier transform of the two things, what we'll do is we'll take the Fourier transform of GR of t. Now this is a continuous time signal. So what Fourier transform I am talking about here? So it's a continuous time Fourier transform. I plug it into the formula G of n HR of t minus nt. Because of the linearity, I take it inside the summation, and also since I'm taking continuous time Fourier transform, Gn is like a scalar for that continuous time Fourier transform. So I get n from minus infinity to infinity, G of n Fourier transform of HR of t minus nt. Okay. Now, what's the Fourier transform of HR of t minus nt? So the Fourier transform of HR is HR j omega, and since this is a shifted version of that, we get the same Fourier transform but with a phase shift of e to the minus j omega Tn. So there is a phase shift of nt. So we plug that in. Now the Fourier transform of that, I'll write gr of j omega, that's n from minus infinity to infinity, g of n e to the minus j omega t little n times hr of j omega. Now hr j omega is not a function of little n, so I can take it outside the summation. So that's hr j omega summation of n from minus infinity to infinity g of n e to the minus j omega t n. That's gr j omega. So let's call this expression 3 star. And now let's compare that to what is it that we are trying to achieve. We are trying to relate the Fourier transform of my discrete time signal with the Fourier transform of my continuous time signal. So let's now write down the formula for the Fourier transform of my discrete time signal, which is g e to the j omega equals summation n from minus infinity to infinity g of n e to the minus j omega n. And let's compare this part of my 3 star formula to this part. What do we see? We see that this part is exactly equal to the Fourier transform of my original discrete time signal, with the only difference that little omega is replaced by capital omega t. Little omega is replaced by capital omega t. So I can plug that in 3 star, and I get that gr of j omega equals to hr j omega times g of e to the j capital omega t. Okay. So what does this expression tell us? If I start with a, so there are, if I start with a discrete time signal and I reconstruct it using a reconstruction filter, any reconstruction filter, then the first thing that is happening is that there is a scaling of the frequency axis. Right? What is the scaling? Let's say if my g of e to the j omega was given by, let's say that this was pi minus pi, this is 2 pi minus 2 pi, so this is little omega axis. You replace this little omega axis by capital omega t. So in the capital omega axis, you divide the axis by, you have to divide the axis by capital T to get capital omega. So this point becomes pi over t. Minus pi becomes minus pi over t. 2 pi becomes 2 pi over t. And minus 2 pi becomes minus 2 pi over t. So the first step that happens is that there is a scaling of the frequency axis by 1 over t. It's just the reverse of what was happening when we were going from continuous to discrete time. In that case, the frequency axis was getting scaled by multiplication with t. Now you are dividing by t. But after you do the scaling, the second step is that you pass it through your reconstruction filter. So this is your first step. The second step is that we pass it through reconstruction filter. Okay. Now if my reconstruction filter was an ideal reconstruction filter, then what will happen? If my reconstruction filter was an ideal reconstruction filter, then its cutoff frequency is pi by t. So it's going to actually throw out all of these other copies, and the main copy will get scaled by, t, because my reconstruction filter has a height of t. So in the case of an ideal reconstruction filter, what happens is we can simply focus on the principal period of g of e to the j omega. We can forget about all the other copies. Then the principal period we scale, and the gr of j omega is simply, number one is we scale axis, frequency axis by 1 over t, and number two, we scale amplitude by capital T. So if we are using an ideal reconstruction filter, then we do the process which is just the reverse of what we saw earlier when we were going from continuous to discrete. We scale our frequency axis by 1 over t. We started with radian frequencies, we go to radians per second. And we scale our amplitude axis by capital T, which is the reverse of what we had done earlier. Okay, so just want to remind that this discussion is only for the case of an ideal reconstruction filter. If that is not the case, then we stay in this case. Then we are in this setting. Okay. Now, in the case of this ideal reconstruction filter, we actually find out that if I have a sequence Gn and I am doing its conversion to continuous time, and I use a time period T1 to get back G1 of T, and someone else does the same thing but with a time period T2 to get back Gt of T, the end result is that G1 of T will not be equal to G2 of T, because the way your frequencies and amplitudes will be scaled will be a function of the time period that you use in your discrete to continuous block, which defines your reconstruction filter. Okay. And as a general rule of thumb, this property, what it means is that if our signal, if our Gn has a discrete frequency little omega naught, then our continuous time signal will have a continuous frequency at, so you have a discrete frequency at little omega naught. That discrete frequency will get converted into a continuous frequency, so that continuous time frequency will be capital omega naught, defined as little omega naught over T. Okay. So let's take a look at a simple example. Let's say that you generate a sequence Gn which is cosine of pi by 3n. Okay. So discrete time sequence, we don't care where it came from. And you pass it through this first block and use T1 equals to 1 over 30,000. And then you pass it through this other block and use T2 equals to 1 over 6,000. So if you have to think about it, let's start with the Fourier transform of cosine of pi by 3n. Right? So the Fourier transform of cosine of pi by 3n, it's going to be an impulse at pi by 3 with an area of pi, and it's going to be an impulse of at minus pi by 3 with an area of pi, and then of course it will repeat itself from minus pi to pi. So after that you will have periodic repetitions. So if you want to understand how this discrete time gets converted to the continuous time, and if we are assuming an ideal low-pass filter, so ideal reconstruction filter, the first thing is you just focus on the principal period. So we just focus on the principal period and we end up with just from minus pi to pi, I have two impulses, one at pi by 3, one at minus pi by 3, and their areas are pi and pi. Now, what this expression says is that once we have selected the principal period, once we have found the principal period, we first scale our frequency axis by 1 over t and also scale our amplitude by t. So when I scale my frequency axis, so if I'm looking at, for the case of t1 equal to 1 over 30,000, when I scale my frequency axis, where will pi by 3 go? So we'll have pi by 3 divided by 1 over 30,000, that will be multiplied by 30,000, so that's 10,000 pi. That's minus 10,000 pi, the other side. Now we are in the capital omega axis, and we have an impulse here and an impulse here. Now, the area of these impulses previously was pi. What will be the area of the impulses now? So one answer you could give is that, well, we wrote here that scale amplitude by t, right? So we should better have this amplitude here, the area here, pi t. But we have to be careful because these are impulses. These are not. So an impulse is not defined by its amplitude. An impulse is defined by its area. Okay? In particular, there is a property of an impulse that if you have an impulse and you scale it by delta AX, then its area actually gets scaled by 1 over AX, 1 over A. Its area gets, it is 1 over A times delta of X. So actually when we were scaling our frequency axis, because we had an impulse, here is an important point to keep in mind. Because we had an impulse, when we scaled the frequency axis, that automatically scaled the area also. And now when we multiply it by t, what happens is that that t gets cancelled. So what we are really getting is we had a scaling of t, and then we multiplied it by t, and so actually our impulses stay the same. Okay? This will be, of course, not the case if we did not have an impulse. If I had a Fourier transform which looked like this, which was not an impulse, then what I described earlier holds. Right? You will then scale the amplitude and you will scale these axes. Okay? But impulse, you have to be careful because impulse doesn't have amplitude. Impulses have areas. Impulses are defined in terms of areas. So now that we have this picture, we can ask, what is G1 of t? So what is G1 of t? This is the Fourier transform of G1 of t. G1 j omega. So what is G1 of t? So G1 of t, using the inverse Fourier transform, it's cosine of 10,000 pi t. So we started with a discrete time signal, and with a cosine with a frequency of pi by 3, and we end up with a 5 kilohertz cosine. So this is case 1. Now the same input signal. The only thing we are changing is change my time period for the conversion to 1 over 6,000. How will my result change? I'm still starting with this. I'm still starting with this Fourier transform in the discrete world. I'm still focusing on minus pi to pi. But now my scaling will be a function of My frequency axis, instead of getting multiplied by 30,000, it will get multiplied by 6,000. So I'll get an impulse at 6,000 pi over 3, which is 2,000 pi. And I'll get an impulse at minus 2,000 pi. And of course, the area will be pi because there is a scaling of frequency axis which gave it pi by t, and then you had scaling of amplitude by t, so that got cancelled. So now my G2 of j omega is this, which means that my G2 of t is still a cosine because I have two impulses at plus and negative frequency, but the frequency of that cosine is now 1 kilohertz. So this just shows that you have an incredible amount of leverage when you start with a discrete time signal to generate whatever continuous time signal you want by just changing the time period that you use in your continuous to discrete converter, in your discrete to continuous converter.